Okay, so we've talked a little bit about coordinate systems. We understand that they're either projected or geographic, and we've talked about what a GCS is and how it comes from and how we use various things to create a datum and whatnot and how that all works through. Now let's talk a little bit about the projected coordinate systems, the PCS. So projections are basically they're mathematical in nature, um, and it's hard to explain how to do it. The way I sort of visualize it is um, taking something clear, like a sheet of clear plastic or something like that, and holding it up to the globe, looking through the plastic to the globe behind it, and then drawing what you see directly behind it as if to trace it. All the while knowing that because the plastic is either wrapped as a cylinder or held as a square plane or in a cone, there's some places it's going to touch perfectly up against the globe, and other places there's going to be some gap. And as that gap occurs, it will distort the size, the shape, and the direction of things that you're tracing because you're just tracing visually what it looks like, as opposed to if you did that and then roll it out or compare it, it's not going to be the same shape exactly. This subtle distortion that comes from taking something round and making it into something flat creates not so subtle problems. So we're going to look at what some of these things are and how this all plays into the notion of projections. We have three basic types: cylindrical, conic, and azimuthal. So imagine my clear plastic wrapped into a tube. That is what you would do to create a cylindrical projection. And then as you look down there in the bottom, sort of looking through the plastic, tracing what you see, then imagine slicing the back of the plastic open and unrolling it, you'll kind of get what you see directly above. And that is North America. In a conic projection, we would sort of roll that plastic into a cone like you would have a tip of ice cream in. And that representation of the planet would then fit inside the cone and touch at some places and some points, but not at others. And then imagine going through and, drawing the outline of the thing that you're interested in, slicing open the back of the cone and unrolling it. It's not going to be square, but it will be flat. And you would get something that looks very much like you see right above it, which is a conic projection of North America. And then we have an azimuthal projection, where basically we would just take a flat plane of plastic like that, touch it down at some point, in this case the North Pole, and then looking down from that, draw what shapes things appear to be. And if you did that, looking at the top, you can see that is what North America would look like. And as you can tell, not only do you get very different looking shapes, things tend to sometimes point in different directions, and certain parts of these maps are exaggerated or more prominent than others. And that can be a problem. So let's look at some of the cylindrical stuff. Cylindrical projections come in one and two sort of orientations. Cylindrical or transverse cylindrical. Cylindrical is up and down, transverse is sideways. The most famous cylindrical projection ever is Mercator. It's been around since the 1500s, and it was really good at preserving direction, and we'll talk more about that later. The current system we use a lot, the UTM system, is the Universal Transverse Mercator. And it's the same concept as what Mercator's was, but instead of having the cylinder in the upright position, it's based off of a transverse cylindrical projection. But there's also other ones like the cylindrical equal area and equirectangular cylindrical projections as well. Conic projection, Lambert and Albers is probably the most common. Equidistance is also pretty common, but it's basically cone unwrapped. Azimuthal are typically polar, but they can be oblique. And this is some examples of some of the different azimuthal projections that are out there. There's also some special ones that I'm not going to talk much about. If you go to any one of these individual projections, there's a whole bunch of parameters that go along with them that allow these projections to be used in lots of different GIS systems. Here, for example, we're looking at the properties of Albers equal area conic, and if you look at the projection parameters, you'll see that we have no false easting or false northing, but we do have a central meridian, and we have two standard parallels and a latitude of origin, and we have the base GCS that this is off of, and then the datum that that GCS is off of, and it's all listed right there. And this is important because it turns out if you want to adjust these, you have to change some of these numbers, and we'll talk about that in another set of slides. So let's talk about what these parts are. What is the central meridian? Okay, the longitude, which serves as the 0 scale on the origin of the map, and x values will come to the right of the central meridian are positive, and to the left are negative. And so it is effectively the prime meridian. The prime meridian runs through Greenwich, England. That is where 0 starts, and as you move to the left towards the US, you have negative numbers. A reference latitude is the point at which from which we measure our north, how far north or south we are, and that is typically going to be the equator. Now, as if not complicated enough, when we have these various projections like cylindrical or conic, and we envision that plastic wrapped around that globe, it can actually happen in two ways. The first is with a single standard parallel. So imagine you draw that plastic down tightly so that it touches the globe at one spot. In this case, in the traditional cylindrical configuration, that's going to be the equator. And at that point, there is no distortion. None. It's perfect. As you move north or south away from the equator, you gradually get more and more and more distortion. But if you look along the edge, the left edge of the image there on the left side of the slide, you'll notice how you can go up and down a ways and you're still not far away from the edge. But then as you start getting up to like the middle of North America or towards the North Pole, there's quite a distance from the edge of that cylinder into the actual surface. That's where the distortions become more increased. Now, I said we had two different flavors of it, if you will. What if you have two standard parallels? Two standard parallels occur if you were to imagine to make that cylinder even smaller to the point where it's smaller than the diameter of the Earth. So it has to enter and exit the Earth's surface at some point. Now, once you do this, instead of having a where everything is perfect, and as you move away from one of these lines, the distortion increases. But if you have the lines properly positioned over an area of interest, you'll have two lines where it's perfect, and you'll have a larger area that's near perfect. And so if you look to the image on the left, there's only so much room above and below that line that's really, really good. But you have that same amount of area above and below the standard parallels on the one on the right, and depending on where you position them, you can end up with a much larger area that's actually quite accurate. We'll talk about false easting and false northing. What do these things do? Well, they don't really do anything. They are arbitrary numerical additions to the coordinate values. And they do them for one reason, and that is to make sure that on a given data set, all the x and y values are positive. Turns out, from a data entry standpoint, it is very easy to forget or to miss adding a negative key stroke in front of a number. And so if we have an arbitrary addition to the values that makes everything come out positive, it actually makes for better and easier data entry, and it saves errors. Coordinate units, these are all based on the various coordinate system types. Now we're going to talk about distortions. All map projections introduce distortion. The type and the degree of distortion varies with the map projection. When you use a projection, you got to take care to pick the one that's suitable for what you're doing. Now, within any given projection, the area that it's designed for, the accuracy is good and the distortions are minimal. But as you look at bigger areas, Areas that fall outside of a particular plane or zone in a projected coordinate system, the distortions become more significant, and then it begins to matter which ones you pick. Some preserve area, some preserve distance, some preserve shape, some preserve distortion. Here is the Mercator projection and the equidistant conic projection. And I want to point out, if you look to the top left, near the center of the image, slightly off to the left, there's a really large landmass, and that is Greenland. If you look to the map on the right, near the center, the tiny little mass that is just below the center and to the left, that is Greenland. Go back over to the one on the left, image on the left that is. Notice where Africa is. Compare the size of Africa to the size of Greenland. Now go over to the equidistance conic, compare the size of Africa to the size of Greenland. See the difference? Mercator distorts distance and area. It preserves the shape of objects and the direction, which Mercator designed that projection for sailing, primarily back in the 1500s. The ability to accurately know which direction to sail to find someplace was important. To know what places looked like, to know where to sail on it to find a particular cove or a river or something was important. Nobody cared how big or small something was, as long as you could find things. And it does a good job of that because it preserves direction and shape. Equidistance conic, it distorts the direction and shape, but it preserves the distance and the area. So if you're trying to compare the size of, for example, Africa to Greenland, this is a better choice. If you want to measure the distance from Africa to Greenland, this is a better choice. Then there's compromise projections. Robinson's a good example of this. Basically, compromise projections distort everything, but only a little bit. So it takes elements from these other projections and combines them in a fashion so that direction's not bad, area is not bad, size is not bad. Nothing's perfect, but more importantly, nothing is horrible. It is a compromise between the four properties. Spatial extents, they indicate the range of the XY values. I've either talked about this before or I will talk about it again. I'm not sure. I can't remember the order I'm recording these. But from that, you can get the idea of where it's at. I want to point out a little something here. When you look at that top one, from 83 to minus 90, minus 180 to positive 180, that's basically the globe. Now the interesting thing is, why does the top not go to 90? Wouldn't that be the North Pole? Well, that would be the extent if we were mapping the oceans. But we're mapping the land masses. It turns out the North Pole is actually on ice. It's not a true landmass, unlike the South Pole.